China just built a machine that could end the steam turbine, the technology behind virtually every power plant on Earth, for 140 years. It sits inside a steel factory, takes up half the space of a conventional generator, and produces 50% more electricity from the same heat, using nothing but pressurized CO2, the gas you exhale with every breath. That one unit turns waste heat, the factory used to vent into the sky, into 70 million kilowatt-hours a year, enough to power nearly 7,000 American homes. You heard that right. One factory's garbage energy, powering a small city. And to understand why that changes everything, you need to know the embarrassing secret at the heart of modern civilization. The embarrassing secret at the heart of civilization. Think about the last time you flipped a light switch, or charged your phone, or turned on your air conditioning in the middle of August. You probably never wondered what mechanical process actually made that electricity. Almost nobody does. And that is exactly how the most embarrassing inefficiency in modern engineering has managed to hide in plain sight for over a century. Here is the truth. Whether your electricity comes from a coal plant, a natural gas plant, a nuclear reactor, or even a concentrated solar facility, the final step that actually generates your power is identical. You heat water. You boil it into steam. You shoot that steam at the blades of a turbine. The turbine spins a generator. Electricity comes out the other end. That is it. That is the process running behind every wall socket in nearly every country on Earth, and it has not fundamentally changed since the 1880s. But here is what nobody talks about. That process is horrifyingly wasteful. For every unit of energy you feed into a conventional power plant, roughly 60 to 65% of it never becomes electricity. It leaves as heat dumped into cooling towers, blown into the atmosphere, or poured into whatever river happens to be nearby. You are not imagining that. The majority of the fuel the world burns to keep the lights on does not keep the lights on. It warms up the sky. Every coal plant, every gas turbine, every nuclear reactor, they are all, at their core, extraordinarily expensive machines for throwing energy away. And the worst part is not the waste itself. The worst part is that the entire world simply accepted it. Governments accepted it. Utility companies accepted it. Engineers accepted it not because they did not care, but because the laws of thermodynamics made it seem like there was no alternative. Water was the working fluid. Steam was the mechanism. And the physics of steam imposed a hard ceiling on efficiency that no amount of clever engineering could break through. You could build a bigger turbine. You could run it hotter. You could increase the pressure. But you were always pushing against the same wall. And every incremental gain cost exponentially more money for diminishing returns. For 140 years, this was the deal. You wanted electricity? You accepted the waste. No country, no company, no engineer had a better answer. But what if the problem was never the turbine? What if the problem was the steam itself? Why steam hit a wall? To understand why steam is the bottleneck, you need to understand one concept that sounds complicated but is actually simple: the Carnot limit. In the 1820s, a French engineer named Sadi Carnot figured out that no heat engine can ever convert all of its thermal energy into useful work. There will always be waste, always. That is not an engineering failure, that is physics. But here is where it gets interesting. The amount of waste depends on the working fluid, the temperatures involved, and the pressures you can achieve. And water, for all its abundance and familiarity, turns out to be a deeply frustrating substance to build a power cycle around. You have to pump enormous energy into water just to get it to change phase, to go from liquid to steam. That phase change eats up a huge portion of the heat you put in before the steam ever touches a turbine blade. Then, once the steam expands and does its work, it drops in temperature and pressure rapidly, and you are left trying to squeeze useful energy out of a fluid that has already given up most of what it had to offer. The result is a hard efficiency ceiling. In a real-world power plant, not a textbook, not a simulation, a real plant burning real fuel. Steam-based systems typically convert about 33 to 38% of their input energy into electricity. The rest is gone. Engineers have spent decades trying to push past that ceiling. They have raised steam temperatures beyond 1100 degrees Fahrenheit. They have increased pressures to supercritical levels. They have added reheat stages and regenerative feed water heaters and every thermodynamic trick in the textbook. And after all of that effort, all of that money, all of those decades of optimization, they have squeezed out maybe 3 to 5 extra percentage points. That is it. The technology is not just old. It is finished. There is almost nothing left to extract from it. And that is the moment you have to ask the uncomfortable question. What if, instead of torturing water into performing slightly better, you threw water out entirely and replaced it with something else? A working fluid so different from steam that it rewrites the rules of what a turbine can do? That fluid exists, and most people have never heard of it. The fourth state of matter you were never taught. You learned this in school. Matter comes in 3 states: solid, liquid, gas. Ice melts into water. Water boils into steam. Simple, clean, easy to put on a chalkboard. And also incomplete. Because there is a fourth state that most science curricula skip entirely, and it happens to be the key to breaking the efficiency wall that steam could never get past. It is called a supercritical fluid. And here is how it works. Take any substance and start raising its temperature and pressure simultaneously. At some point, you hit what physicists call the critical point, a specific combination of heat and pressure where the substance stops being classifiably liquid or gas. It becomes both at the same time. It has the density of a liquid, meaning it can carry enormous amounts of energy in a small volume, but it flows with the freedom of a gas, meaning it moves through machinery with almost no resistance. It is, thermodynamically speaking, a dream working fluid. And the substance that happens to do this better than almost anything else on Earth is one you already know: carbon dioxide. Here is what makes CO2 almost suspiciously perfect for this job. Its critical point sits at just 88 degrees Fahrenheit and about 1,070 pounds per square inch of pressure. Those numbers might sound extreme, but in the world of industrial engineering, they are remarkably tame. Steam power plants already operate at temperatures and pressures far beyond that. So, reaching the critical point of CO2 does not require exotic conditions. It requires conditions that existing industrial equipment can already handle. But the payoff for crossing that threshold is enormous. Once CO2 enters its supercritical state, it becomes nearly as dense as liquid water while behaving like a gas. That means you can push it through a turbine and extract massive amounts of energy from a machine that is a fraction of the size of a conventional steam turbine. You are getting more power from less equipment, using less physical space, with fewer moving parts, and the efficiency numbers reflect exactly that. Where steam maxes out around 35 to 38% in the real world, a supercritical CO2 cycle can theoretically push between 45 and 50%. That is not a modest improvement. That is not an incremental gain squeezed out after decades of optimization. That is a generational leap, the kind of jump that does not come along more than once or twice in a century. So if you are sitting there thinking, this sounds too good to be true, you are not wrong to be suspicious, because scientists have known about supercritical CO2's potential since the 1960s. They have known the math works. They have known the physics checks out. And for 6 straight decades, not a single team on Earth managed to turn that beautiful theory into a working commercial machine. The reason why is an engineering nightmare that nearly killed the technology entirely. The 60-year engineering nightmare. Imagine you are an engineer in the 1960s. You have just run the numbers on supercritical CO2 as a working fluid. The thermodynamics are gorgeous. The efficiency gains are obvious. You can see clearly on paper that this substance could outperform steam in almost every measurable way. You walk into your lab convinced you are about to change the world. And then you try to build the machine. And the machine tries to destroy itself. The first problem is the CO2 itself. At supercritical temperatures, we are talking 600, 700 degrees Fahrenheit, and above, carbon dioxide stops being chemically passive. It becomes aggressive. It starts attacking the metal alloys that your turbine blades are made of, eating into them through a process called carburization. where carbon atoms from the CO2 physically migrate into the metal's grain structure and weaken it from the inside. Your turbine does not fail in a dramatic explosion. It fails slowly, invisibly, as the blades corrode and degrade hour by hour until one day they simply cannot take the stress anymore. Conventional steel alloys, the ones that work perfectly well inside, steam turbines fall apart in a supercritical CO2 environment, so you need new alloys, exotic, nickel-based superalloys. Ceramic coatings that can survive chemically hostile conditions for tens of thousands of operational hours without degrading. Materials that, in the 1960s and 70s, either did not exist yet or could not be manufactured at the scale and precision required. But the materials problem was only the beginning. The second nightmare is the heat exchanger, the component called a recuperator that makes the entire efficiency advantage possible. The supercritical CO2 cycle depends on recycling its own waste heat internally. Hot CO2 leaving the turbine passes its remaining thermal energy to cold CO2 entering the cycle, so less external heat is needed to bring the fluid back up to operating temperature. That is where the efficiency magic happens. But building a recuperator that can handle this job is a manufacturing challenge unlike almost anything else in industrial engineering. You need channels narrower than a human hair, chemically etched into metal plates with microscopic precision, then diffusion-bonded fused at the atomic level into solid blocks of metal that must withstand over 200 atmospheres of pressure without leaking. A single flaw in a single channel can cascade into a system failure. The tolerances are not tight, they are punishing. And then came the third problem, the one that frustrated engineers perhaps more than any other. The bearings. A supercritical CO2 turbine spins, at extraordinary speeds in some designs, north of 50,000 revolutions per minute. At those speeds, conventional oil-lubricated bearings are useless. Not just because of the mechanical stress, but because supercritical CO2 dissolves into lubricating oils, contaminating them and destroying their protective properties. Any oil that leaks into the working fluid contaminates the entire closed-loop system, so you cannot use oil, which means you need bearings that function without any physical lubrication at all. The solutions that eventually emerged: gas foil bearings that ride on a thin cushion of CO2 itself, magnetic bearings that suspend the rotor shaft in mid-air using electromagnetic fields with no physical contact whatsoever, are each an entire engineering discipline unto themselves. Each one took decades to develop to the point of reliability. So there it was, 3 separate, brutally difficult engineering problems: materials, heat exchangers, and bearings, each one capable of killing the technology on its own. For 60 years, research teams around the world chipped away at them in isolation. A materials breakthrough in one lab, a bearing prototype in another, a recuperator design in a third. But nobody solved all 3 simultaneously, at commercial scale, inside a single integrated machine connected to a working electrical grid. Nobody, that is, until December 2025, inside a steel plant in a Chinese province that most people reading this could not point to on a map. Chaotan One, the moment it stopped being theoretical. Picture a steel plant, not sleek, not futuristic industrial, furnaces roaring at temperatures that would melt the frame of your car, molten metal moving through production lines that have not changed much in decades, and everywhere, heat. Enormous, relentless quantities of heat pouring off sinter machines, blast furnaces, and cooling lines, heat that has no purpose, no destination, no value. For the entire history of steelmaking, that heat has simply been vented into the atmosphere. It is the exhaust of an industry that accounts for roughly 7% of global CO2 emissions, and nobody has ever found a commercially viable way to do anything meaningful with it. Until now. In December 2025, China's National Nuclear Corporation switched on a unit called Chaotan One at the Shugang Shuicheng steel plant in Liupan Shui, a city in southwest China's Guizhou Province. And with that switch, the supercritical CO2 power cycle stopped being a laboratory concept and became a commercial reality, not a prototype. Not a demonstration loop running in controlled conditions with a team of researchers watching every gauge. A real, Grid-connected power generation system producing real electricity sold to a real electrical grid, operating inside a working steel factory that did not change a single thing about its production process to accommodate it. Here is what Chaotan One actually does. It captures the waste heat streaming off the plant's center exhaust heat that was previously just dumped into the air and uses it to drive a supercritical CO2 Brayton cycle. Carbon dioxide is compressed to high pressure, heated by that waste exhaust in a series of heat exchangers, expanded through a compact turbine to generate electricity, then cooled and recompressed in a continuous closed loop. No combustion, no water, no steam, no additional fuel of any kind. And the numbers are not theoretical, they are operational. Chaotan One generates over 70 million kilowatt-hours of electricity per year. It adds roughly $4.26 million in annual revenue to the steel plant's bottom line. It increased net power generation by over 50% compared to the conventional steam-based waste heat recovery system it replaced. And it did all of this while occupying 50% less physical space. The factory did not slow down. It did not retrofit its furnaces. It did not alter its product. It simply stopped throwing away energy. Now here is the part you need to pay attention to, because it reveals how deliberate this move was. China's National Nuclear Corporation did not install Chaotan One at a nuclear power station. They did not plug it into a coal plant. They chose a steel factory, and that choice was not an accident. A waste heat recovery unit at a steel plant is the perfect proving ground. The heat source is abundant, consistent, and already there whether you use it or not. The stakes of a shutdown are commercial, not civilizational. If the unit trips offline, the steel plant keeps running, and nobody loses power. It is a low-risk, high-reward environment, specifically designed to do one thing: accumulate real operational hours, validate materials under sustained load, and generate the kind of reliability data that no laboratory loop, no matter how sophisticated, can ever provide. And here is what makes this story even more remarkable. Almost nobody in the Western world covered it. Not because it was classified or hidden, it was announced publicly by Chinese state media, covered in Chinese engineering journals, and presented at international energy conferences. It was simply ignored. Treated as a niche industrial story from a province most Western journalists could not find on a map. But ignoring Chaotan One does not make it less significant. It just means the significance is building while no one is watching. And that brings up the question you are probably already asking. If this technology is so transformative, why is it not already everywhere? What this does not mean yet. Here is where you need to resist the urge to get ahead of the story. Because the difference between hype and a genuine breakthrough is honesty about what has actually been proven and what has not. Chaotan One is real. It works. It is generating electricity and revenue right now. But it is not replacing the primary turbines in nuclear power stations. It is not powering cities. It is not yet operating at the temperatures, pressures, or scales that would be required to serve as the core generation cycle inside a large coal, gas, or nuclear plant. What it is doing is recovering waste heat in a relatively forgiving industrial environment, and that distinction matters. The materials science questions that serious infrastructure decisions depend on are still open. How do those nickel-based superalloys and ceramic coatings perform after 5 years of continuous operation? After 10 years? After 50,000 hours under sustained thermal and chemical stress? Nobody knows, because the only way to answer those questions is to run the machine and wait. There is no simulation that can substitute for time. The recuperator, that intricate heat exchanger with channels narrower than a human hair bonded into solid metal blocks, has never been tested at this scale for this duration in a commercial setting before. Its longevity data does not exist yet because it could not have existed until a unit like Chaotan One started operating. The bearing reliability statistics that grid operators and utility executives and national energy planners require before committing billions of dollars to a new generation platform, those numbers are being generated right now, hour by hour, inside that steel plant in Guizhou. But they are nowhere close to the threshold that would satisfy the kind of institutional decision-makers who control the world's power infrastructure. These are people who think in decades, not quarters. They do not adopt a technology because it is promising. They adopt it because it is proven, at scale, over time, with failure rates they can model and insure against. So if you are waiting for supercritical CO2 to replace every steam turbine on Earth next year, you will be disappointed. The gap between where this technology is today and where it needs to be to displace steam at the center of baseload power generation is real, and closing it will take years, likely another decade of sustained operational data, iterative design improvements, and the slow accumulation of institutional trust. But here is the thing about that gap. It is exactly the same gap that every transformative energy technology in history has had to cross. And the machine that ended up powering the modern world faced it too. The steam turbine did not change the world overnight either. If you want to understand where supercritical CO2 is headed, you need to understand where steam has already been because the pattern is identical. In 1884, a British engineer named Charles Parsons demonstrated the first practical steam turbine. It was small, limited, and wildly impractical by modern standards. Nobody looked at that early machine and said, "This is going to power every city on Earth." It was a curiosity, a proof of concept, a promising idea with 1,000 unsolved problems standing between it and widespread adoption. The metallurgy was not ready. The manufacturing tolerances were not there. The institutional trust did not exist. Utility companies were not going to rip out their existing reciprocating steam engines and bet their entire infrastructure on an unproven device because one demonstration went well. So what happened? Time happened. Engineers ran the machines. They collected data. They found the failure points and fixed them. They improved the alloys, refined the blade geometries, tightened the tolerances. Each generation of turbine was slightly better than the last, slightly more efficient, slightly more reliable, slightly cheaper to build and maintain. Investors noticed. Utilities noticed. Governments noticed. And at some point, not overnight, not in a single dramatic moment, but gradually, and then all at once, the economics became undeniable. Steam turbines were not just better. They were so much better that continuing to use the old technology became indefensible, and within a few decades, they were everywhere. Every transformative energy technology in history follows this exact curve. Invention, proof of concept, early commercial deployment in forgiving, low-risk environments where failure is tolerable, accumulation of real-world operational data, cost learning curves that drive prices down as production scales up, and then rapid sweeping displacement once the economics tip past the point of no return. Chaotan One is the early commercial deployment phase. That is exactly where supercritical CO2 sits right now. Every hour that machine runs inside that steel plant in Guizhou is an hour of real-world performance data that no simulation, no laboratory loop, no computer model can replicate. That data feeds directly into better designs. Better designs attract more investment. More investment funds larger units at higher temperatures and greater pressures. Larger units generate more data. And that feedback loop, once it starts turning, tends to accelerate in ways that catch everyone off guard. The question is not whether supercritical CO2 will follow this curve. The question is how fast. And that is what makes this moment genuinely different from everything that came before it. Right now, as you are listening to this, a machine inside a steel factory in a Chinese province most of the world has never heard of is quietly doing something that no machine in human history has done, generating commercial grid-connected electricity using supercritical CO2 instead of steam. Not in theory, not in a press release, not in a render on someone's conference slide. Right now, the device powering your home is functionally identical to something built in the 1880s. The device running inside that steel plant is not. It is smaller, it is more efficient, and it runs on the gas you just exhaled. The steam turbine ruled for 140 years because nothing could challenge it. Something finally has. And it is already running.